Okay, so lesson 2, solving second degree trigonometric equations. So now we're solving second degree equations, which means we have things like sine squared in there and not just sine or cosine or tangent anymore. So to do this, we first going to do a quick factoring practice. So factoring trigonometric expressions is the same as factoring anything else. Just looks different because there's trigonometric expressions in there. So for a, we have 8 tan a plus 4. The only thing in common between these two is a factor of 4. So we can factor that out, put it out front, divide each term by 4. Gives us 2 tan a plus 1. So that would be the factored form of that one. The next one, sine squared x minus 3 sine x. So now the thing that's in common between both terms, the greatest common factor, is sine x. So I can write that out front. Now divide each term by sine x. Well, sine squared x is really sine x times sine x. We just write it this special way, so we don't need to write brackets all the time. So when I divide out 1 sine x, I'm left with sine x here. 3 sine x times sine x divided by sine x gives me 3. Okay, this one's a little bit different. This is actually a difference of squares here, because 4 is a perfect square, sine squared is a perfect square, and 1 is a perfect square. So you can factor this like any other difference of squares by taking the square root of the first term plus the square root of the second term times the square root of the first term minus the square root of the second term. D cos squared x minus 3 cos x minus 28. When you're factoring these, it might be simpler to think of this as just this trinomial. So think of it as factoring x squared minus 3x minus 28. So you're looking for two numbers that multiply to minus 28 and add to minus 3, which would be negative 7 and 4. But we didn't really start with x, we started with cosecant x. So our two factors are cosecant x minus 7 and cosecant x plus 4 are your two factors. So this is another one. You could think of this one as 2x squared minus 7x minus 4. So this one's a little bit harder to factor. We're looking for two numbers that multiply to negative 8. That's the 2 times the negative 4, and add to negative 7. Sorry, to positive 7. So now I use those two numbers to split up the middle term. So I can use 8x minus 1x. Factor out the greatest common factor from each pair of terms. Oops, plus 4. Here the only thing I can factor out is a minus 1. This makes my two factors 2x plus 1 and x plus 4. But I didn't start with x there, I started with cos of x. So my two factors are 2 cos x plus 1 and cos x plus 4. So now we practice factoring because we are going to need this when we're solving these second degree equations algebraically. Okay, moving on. So now we're going to start solving some equations. It starts with solving them graphically. So we have the equation 2 sine squared x equals 1 minus sine x. Use a graphical approach to determine the roots of the equation, where x is between 0 and 2 pi. And it wants to give solutions as exact multiples of pi. So the problem with when it wants us to give exact values of pi, our calculator can't give us radians with exact values of pi, but it can give us the exact values in degrees, and then we can change it. So I would start by solving this in degrees. So remember, you need to change your TI inspires so that you're graphing in degrees. So you got to change it in two spots. And you have your option. You can either graph 2 sine squared x in F1 and 1 minus sine x in F2, or you can bring it all to one side and find the x-intercepts. That's completely up to you. So I prefer the intersection method, so I usually graph the one in F1 and the other one in F2. You're going to get something that looks like this. So 2 sine squared x looks like this. Comes down back here and looks like this is about 180 degrees and this is 360 degrees. So this is 2 sine squared x. And then our second side of the equation, 1 minus sine x, you can graph in F2. And that looks like this. And this keeps going off our screen. So this is 1 minus sine x here. So your solutions come at all of these points of intersection. Okay, so when you find these points of intersection, you should find that this first one happens at x equals 30 degrees, the second one happens at 150 degrees, and the last one happens at 270 degrees. But we wanted to answer in radians, so now I'm going to take each of those times by pi over 180. So remember, if you want to work in exact values, just type this part into your calculator, 30 divided by 180. That's going to give you the fraction 1/6, and then you know it's pi over 6. So if you do that for each of these, when you convert 150, so we know the first one's pi over 6. When you do that same thing with 150 degrees, you get 5 pi over 6. And when you do that with 270 degrees, you get 3 pi over 2. So those are your two solutions. I'm stopping there because it told me within 0 and 2 pi. That's also why it would probably been a good idea to set your window with a maximum value of 360 degrees so that you don't see more and more and more solutions there to use. The general solution, well, we see here that this graph goes here. It looks like it, and combined with this graph, has a period of 2 pi. So these are happening every 2 pi degrees, or 360 degrees. So our general solution will be x equals pi over 6 plus 2 pi n, 5 pi, ooh, that's funny, 5 pi over 6 plus 2 pi n, and 3 pi over 2 plus 2 pi n ran as an integer. So these ones aren't as obvious what this will be because we have multiple functions here. But if you were to just look at all the way up to 4 pi, you'd see that these are repeating in the exact same spot. So if you graph it up to 720 degrees, you'd see that this pattern repeats exactly 360 degrees apart. Okay, so example 3 asks us to do the exact same question algebraically. So we already know what answers we're going to get because we just did it, but now we're going to see how we can do it algebraically. So just as if I was solving a quadratic equation, I'm going to move everything over to one side and make the other side equal to 0. And just like a quadratic equation, I'm now going to factor this. So I'm looking for two numbers that multiply to -2 and add to 1. And then I'm going to use that to split up the middle term. So whether you want to leave the sign in there while you factor or replace it with just an x, doesn't really matter. Okay, so now I'm going to keep factoring this. Look for my factor by grouping. The greatest common factor between those first two terms is sine x. That gives me 2 sine x minus 1. The next two terms don't have a common factor greater than 1, so I can just take out a 1. This tells me my factored form is 2 sine x minus 1 times sine of x plus 1. Now, solving a quadratic equation, we'd now set each factor equal to 0 and solve for x. So that's exactly what we're going to do. So I'm going to have 2 sine x minus 1 equals 0. And sine x plus 1 equals 0. And now I need to solve each of these equations. So I'm going to get sine by itself here. So this gives me sine x equals 1/2. So that means sine's going to be positive in either of these quadrants. To find your reference angle, you can go to your unit circle, your special triangles, use the sine inverse function. We want to know these as exact values. So if you're going to your calculator and using sine inverse, you want to make sure you're in degree mode and then changing it to radians. You will find that your reference angle in radians is pi over 6. So that means the two solutions from this factor are pi over 6 and 5 pi over 6. Remember, this arm would be 6 pi over 6, but we're 1 pi over 6 short of that. For the second factor, we're going to move over that 1. Sine is negative in the bottom two quadrants here. And we're going to find a reference angle of pi over 2 for 1. So that means our only angle here would be this angle, which is 3 pi over 2. Then we can bring together all of our solutions and we can say x is pi over 6, 5 pi over 6, and 3 pi over 2. State the general solution. Well, again, these are going to repeat every cycle through, so it's the same as the last one, each one plus 2 pi n. Example 4. Use an algebraic procedure to determine the roots of the equation on the given domain and write the general solution. So 4 sine squared a minus 1 equals 0, and we were looking for answers between 0 and 2 pi. So this is a difference of squares. So our two factors are this. So now I need to solve for each factor. What value of a makes each factor equal 0? So I'm solving sine of a to be 1/2. I just did that in the previous question, and I found it was pi over 6 and 5 pi over 6. This one, I'm going to subtract 1 from both sides, divide by 2. Well, it's going to have the same reference angle as the last one, which was pi over 6, but now sine is negative, so I'm going to be in these two quadrants. So remember, this arm was 6 pi over 6, so 1 further would be 7 pi over 6. This arm is 12 pi over 6, so 1 back is 11 pi over 6. So these are the 4 solutions. The general solution, there's no horizontal stretch in this question, so it's going to be every 2 pi n. So the general solution would be pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n, 7 pi over 6 plus 2 pi n, and 11 pi over 6 plus 2 pi n, where n is an integer. That would be the general solution. B, tan squared x plus tan x equals 0. So now I can factor out the common factor of tan x. And then I'm going to solve for each factor. So where is tan x equal to 0? So remember that tan is sine divided by cosine. So tan of x will be equal to 0 wherever sine is equal to 0. And that is at 0, pi, and 2 pi. So you could again use that by using your inverse tan. It's going to give you a reference angle of 0, which is going to tell you that you're going to have reference angle 0 degrees, so it's going to be laying on the x-axis. You can also think of it as your unit circle. Your y value is your sine. So wherever your y value is 0, tan must be 0, and that would be along the x-axis. And we're going to find where's tan of x equal to -1. So this is going to be where your sine and your cosine angles are equal but have opposite signs. So that would be a reference angle of 45 degrees, or pi over 4. Again, you could find that by using your inverse tan or your unit circle. Then we need to figure out which quadrant we're in. We'd be here or here. So the two angles there would be pi over 4. Or sorry, we want tan to be negative, so I'm in the wrong quadrants. tan to be negative, so we should be here or here. So it would be 3 pi over 4. For this quadrant, 3 pi over 4. And the second solution would be 7 pi over 4. So between 0 and 2 pi, we have 5 solutions. Our general solution this time, well, this solution can be described as every pi radians. So one general solution will just be pi n. That describes those. 3 pi over 4 to 7 pi over 4 are exactly pi units apart. That is the period of the tan graph. So the second one we could describe as 3 pi over 4 plus pi n, where n is an integer. That would be our general solution. Okay, so example 5a, determine the zeros of the following functions on the specified domain. So here we have cos squared x minus 3 cosecant, x minus 28. And we're just looking for solutions between 0 and 180 degrees. And we want to answer to the nearest degree. So whenever we see this, that means it's not looking for an exact value. So we can rely a little bit more on our calculators than usual. And really, if you're just asked for this, you could solve this by graphing, but we'll step through it algebraically. So I need to factor this. We did factor it at the beginning. So we're multiplying to negative 28 and adding to negative 3. So that gives us this. And we're looking for the 0, so we're going to make it equal 0. We now need to find the 0 of each factor. So we get cosecant x equals 7. Now we know we can't use that cosecant button on our exams, so it's much easier to change this to sine. So we know that cosecant is 1 over sine. So 1 over sine must be 7. If I take the reciprocal of both sides, that tells me sine of x must be 1 over 7. Now, sine is positive, so I'm going to have one solution from quadrant 1 and one solution from quadrant 2. I just use my inverse function here to find out my reference angle, because I don't need an exact value. And I find a reference angle to be 8 degrees. So this angle is 8 degrees in quadrant 1. In quadrant 2, I'm going to have to go 180 minus 8, which is 172 degrees. So that's from our first factor. Our second factor of cosecant x minus 4, that means 1 over sine x equals negative 4. So that means sine x must be negative 1/4. Now you could find your reference angle here and go through this, but we only needed to know the answers between 0 and 180 degrees. So that's in quadrants 1 and quadrant 2. Sine is not negative anywhere in that domain. So there are no solutions here we need to find on this domain. So you can find solutions for this. We just don't have to for this question because it's not between 0 and 180. B, 2 cos squared theta plus 5 cos theta minus 3 between negative pi and pi. So again, we're going to start by factoring this. So we can split up that middle term into 6 cos theta and minus cos theta because we want to multiply to negative 6 and add to 5. Factor by grouping. Sorry, this one shouldn't be squared. So 2 cos theta minus 1 times cos theta plus 3. So now we got to solve or find the zeros for each factor. So cos theta equals 1/2. So I want to find solutions between negative pi and pi. So this is really a full rotation, except I want to describe anything in quadrant 3 and 4 as a negative angle, and anything in quadrant 1 and 2 as a positive angle. So cosine is positive here and here. And if you were in degree mode and you found your reference angle, you'd get 60 degrees. It's asking between pi and 2 pi, so that does mean we want to work in radians, but your reference angle of 60 degrees means a reference angle of pi over 3. So this solution would be positive pi over 3. That solution would be negative pi over 3. Second factor. Cos theta equals negative 3. This has no solutions. Our minimum value of our cos graph is negative 1. It never equals negative 3. So this just has no solutions. No matter what domain you're solving on, that would have no solutions. So these two are your answers.